Hey everybody, this is the lecture on section 6.2, which is on orthogonal sets. So, definition. Vectors v1 to vm in Rn form an orthogonal set when every pair of vectors is orthogonal. Vi dot vj is 0 for all vectors vi not equal to vj. No vector is orthogonal to itself, of course, so every pair of vectors is orthogonal. So, for example, in R3, so here are two sets. So just the elementary vectors by themselves, those are orthogonal. Form an orthogonal set, right? Every pair's dot product is 0. And here's one little less trivial than that. 1, 1, 1, 1, negative 1, 0, and then 1, 1, minus 2. Okay, those form an orthogonal set. You can check the dot product of any two, and you get 0. This one is 1 minus 1 plus 0 is 0. 1 minus 1 plus 0 is 0. And then 1 plus 1 minus 2 is 0. Okay, the neat thing about orthogonal sets is the following. Consider a linear combination of an orthogonal set. So W is equal to A1V1 plus AMVM. What is AI? Okay, if we take, so let's show that. The coefficient AI in the linear combination is W dot VI over VI dot VI. Okay, well, take the dot product of VI with this. So W dot VI is equal to A1V1 plus, now let's include AIVI, which may be at the beginning or end or somewhere in the middle. But we'll just put it in the middle for effect. Dot VI. As we did when discussed in section 6.1, the dot product distributes over addition, and you can factor out constants. So it becomes A1 V1 dot VI, plus AI VI dot VI plus AM VM dot VI. But since the V's are an orthogonal set, all of these dot products are 0, except for V dot itself. So W dot VI is equal to 0 plus AIVI dot VI plus 0 and 0. Vi is orthogonal to all the other vectors except itself. So what we get in the end here is that W dot Vi over Vi dot Vi is equal to AI, right? Which is what we wanted. Now there are a couple very interesting consequences. Well, there's another interesting consequence of this. So let's write it down as a theorem. Okay, if V1 to Vi, or Vm, is an orthogonal set, and, well then, 1. If W is equal to A1V1 plus ANVAM, then AI is W dot Vi over Vi dot Vi. 2, in particular when W is 0. When W is 0, what? AI is, well, that's 0. When W is 0, this must be 0. So the only solution to the linear combination equal to 0 is the trivial solution, all zeros. That means V1 to Vm are linearly independent. Must be. Okay, well, we did the proof of part 1. Part 2, we're just saying it here. So proof 1 is above. 2, if 0 is equal to A1V1 plus AMVM, then AI is equal to 0 dot Vi over Vi dot Vi, which is 0. So the only solution, the only linear combination equal to 0 is the trivial solution. To V1 Vm times x equal to 0 is a trivial solution. So the vectors are independent. So let's take an example. So let's go back to that orthogonal set that we have up here. 3 vectors. So I got 3 vectors in R3. So they're linearly independent. So this orthogonal set of 3 vectors in R3 is linearly independent. Right, since the dimension of R3 is 3, these vectors must therefore span and be a basis. Okay? So every vector in R3 is a linear combination of these guys. Sorry, flies bother me. So every vector in R3 is a linear combination of these vectors. And now we can solve without doing row reductions. So we can find the linear combination without row reductions. Without row reductions anymore. So for example, right, so we'll say, a nice example picked out here, 1, 1, negative 2. So we have x1 times 1, 1, 1 plus x2 times 1 minus 1 plus x3 times 1, 1 minus 2 equal to 3, negative 1, negative 1. Find x1, 2, and 3. Okay, well, just do those dot products. x1 is equal to 1, 1, 1 dot 3 minus 1 minus 1 over 1, 1, 1 dot 1, 1, 1. x2 is equal to, let me copy that, see if I can save myself some writing. Oops, no, I want to leave that. So vector 2 here and vector 3. So 1 minus 1, 0. 1, 1 minus 2. This is x2, x3. Okay? So that vector is the w, right? And then this is v1.w over v1.v1. v2.w over v2.v2. v3.w over v3.v3. So we get that x1 is equal to 3 minus 1 minus 1 is 1 over 3. x2 is equal to 3 plus 1 is 4 over 1 plus 1 is 2. So it's 2. And x3 is 3 minus 1 is 2 plus 2 is 4 over 1 plus 1 plus 4, 6. 2/3. So let's check. So those vectors are right here. So 1/3, 2, and 2/3. So I have 1/3 plus 2 plus 2/3. Right? 1/3 plus 2 plus 2/3. So 1/3 and 2/3 is 1, so I get 3. 1/3 minus 2 minus 2/3, or plus 2/3. So 1/3 plus 2/3 minus 2. So that's 1 minus 2 is negative 1. Then I have 1/3 minus 4/3. So it's minus 3/3 minus 1. All right, pretty neat. No row reductions, just dot products. Okay, so that's orthogonal sets. Here's another thing you can do with orthogonal sets. It's called projection. Take any vector v and some other vector. Well, take vectors v and w. Okay, v and u. Sorry, we'll call it u. Take vectors v and u. Define the projection onto u of v. The projection of v onto u. And this is going to be equal to v dot u over u dot u times vector u. This is all scalars, and that's a vector. All right, is the projection of v onto u. Projection of v onto u. And orth u is going to be equal to v minus the projection. Is the orthogonal component of v with respect to u, or the component of v that is orthogonal to u, we'll call it that. Say that way. The component of v that is orthogonal to u. And we call it that because it is. This is in the direction of u because it's just a multiple of u, and this will show is actually orthogonal to v. That is orthogonal to u. Sorry. Okay, so theorem. The projection of u onto v, the projection of v onto u is in the direction of u. And the orthogonal component of v orthogonal to u is orthogonal to u. All right, just because you call it the orthogonal doesn't mean it actually is. You have to show it. All right, so we show it, and that's why we call it that. All right, saying things doesn't make it so. You actually have to prove it. So proof. Well, because the projection of v onto u is u dot v over u dot u times u is a multiple of u. Right? It is in the direction. In the direction of u. Okay, and now consider u dot the orthogonal component, the component of v orthogonal to u. This is equal to u dot well, the orth is V minus this projection. So that's by definition. Okay, so this equality here is by definition. So this is u dot v minus u dot the projection onto u of v. So this is equal to u dot v minus u dot, and what is the projection? It's u dot v over u dot u times u, which is equal to u dot v minus, and this is just a scalar, so you bring it out front, u dot v over u dot u dot u. So that cancels. Scalars, they cancel. Dot product is a scalar. So this is equal to u dot v minus u dot v, which is 0. Right? So u is orthogonal to orth u v. Okay? Now, one thing to notice, okay, is the following. So here's V. Let's make V large and make U kind of small. So there's V and U. Right, so here is U, the projection onto U of V. And here is the orthogonal component of V, the component of V orthogonal to U. These two vectors, projection and orthogonal, are both, well, they're orthogonal to each other. Okay, they're orthogonal to each other. 1, right? Orth u v and proj u v are orthogonal. 2, they span the same plane as u and v. So this is the beginning of something known as the Gram-Schmidt process, which is going to be the last topic that we cover, and we'll have a video up on that soon. So we'll do a combined presentation on section 6.3 and 6.4, just so we can get to that Gram-Schmidt process and see how that works. Okay? But this is just the beginnings of it, so we'll do more examples of it later. Okay, one final topic in this section. So, an orthogonal set is an orthonormal set. That's a cool word. So an orthogonal set's a set of vectors that every two are orthogonal to each other. You call an orthogonal set an orthonormal set when every vector in the set is a unit vector. That is, every vector has length 1. Well, once you have an orthogonal set, getting an orthonormal set is easy. So observation. If V1 to Vm is an orthogonal set, then just scale them. 1 over length V1 times V1. 1 over length Vm times Vm is an orthonormal set. So for example, like that orthogonal set that we had back up top in R3, there it is. So for example, this is an orthonormal set, or an orthogonal set, with lengths, right? What are the lengths? Well, square root 3, not plus, square root 2, and square root 6. Right, remember, what's the length of a vector? Remember, the length of V is equal to square root of V dot V. Right, so just dividing those guys by their lengths, 1 over root 3, 1 over root 3, 1 over root 3, 1 over root 2 minus 1 over root 2, 1 over root 6, 1 over root 6, minus 2 over root 6 is an orthonormal set. Right, and when you have an orthonormal set, so if U1 to UM is an orthonormal set, then 1, if W is equal to A1U1 plus AMUM, then now AI is just equal to W dot U, because U dot U is equal to, is the length of U squared is equal to 1. So it's just that now. It's pretty cool. 2, they're linearly independent still, of course. Right, so now, final theorem in the section. First definition. An orthonormal basis for Rn is a basis that is an orthonormal set. Theorem. If U is an n by n matrix, then U inverse is equal to U transpose if and only if the columns are U are an orthonormal basis for Rn. That's pretty neat. So no longer with orthonormal matrices, so whose columns are an orthonormal basis, no longer do you have to do row reductions for anything. Not for finding the inverse, not for finding coefficients in a linear combination. It's all just dot products. And the inverse, even easier, it's just transpose. Right? The proof is basically this. Entry in row I, column J of U times U transpose is the dot product of column I and J of U. Right? This is 1 when I equals J and 0 when I is not equal to J. And that's essentially the whole detail in the proof. So, for example, we had that orthonormal basis. Where did it go? There it is. So this is an orthonormal basis for R3. So just turn it into a matrix. And the inverse of this matrix is just the transpose. Columns become rows. Then 1 over root 6, 1 over root 6 minus 2 over root 6. Pretty neat. Pretty neat. Okay, so that's the lecture for section 6.2.